Welcome back, everyone. Today we're going to continue our conversation on vectors, and in fact, we're going to look at vector spaces today. So, what is a vector space? Well, for the purposes of our conversation, it's a collection of vectors and or functions and or matrices, well, I shouldn't say and or, vectors or functions or matrices that can be added, and multiplied and combined in the same way vectors get added and scaled. Now, that's not a definitive definition, but in this class, I don't think to be successful we need a complete definition of what a vector space is. Just know that they're functions or matrices, vectors, functions, or matrices that get added and scaled like vectors. So an example we looked at last video is R3. Okay, we described that R3 was the set of all vectors with three components with real number elements or components. Okay, another example of a vector space would be the set of all 2x3 matrices. Okay, so looking at these two first examples, you could think of the first example as the set of all vectors that look like A, B, and C, where A, B, and C are all elements of the reals. Okay, they're all real numbers. Okay, what do the 2x3 matrices look like? And again, all I'm giving you right now is the generic representation of elements in this set. Say, well, 2x3 matrices look like A, B, C, D, E, F. Okay, so there's nothing that says that any of these real numbers have to be tied to one another. So that's why there's 6 independent values in this 2x3 matrix that has 2 rows and 3 columns. Next, the set of all functions that are, I said continually, I meant continuously twice differentiable on the interval from -1 to 1. That is going to be denoted C2. So functions that are continuously twice differentiable on the interval from -1 to 1. I know that looks like a square right there. It's not meant to. It's just the interval from -1 to +1, including both endpoints. So that's, I think, maybe a little bit clearer way to denote that. To become familiar with that sort of group, okay, the function f of x equals sine x is in C2 of -1 to 1, but g of x, which is the absolute value function, is not. Okay, the reason why it's not is this is not continuously twice differentiable, because think about it, if you were to take the derivative of g of x, okay, I'm just working on my scratch piece of paper here. If g of x is the absolute value x, which looks like this function, okay, g prime of x is a piecewise function. It's -1 for x is less than 0. It's +1 for x is greater than 0. And it does not exist for x equal to 0. Now, clearly, g prime is not a continuous function. Okay, it looks something like this. -1, open, open, +1. And that's not a continuous function. So, therefore, it's not, g of x is not an element of C2 from -1 to 1. G of x is in C0 of -1 to 1. So that's continuously, well, it's not differentiated. This is the set of continuous functions on the interval from -1. You can clearly see that before taking any derivatives, g of x, the absolute value function, is a continuous function. Whereas f of x, which is sine x, is in C infinity of -1 to 1, because the sine function is continuous and all of its derivatives are continuous. No matter how many derivatives you take of sine x, whether it's 1, 2, 3, 4, or infinite, that derivative is going to be continuous on the interval from -1 to 1. All right. So that's kind of what we're referencing here. The set of all polynomials of degree 3 or less. Okay, let's take a look at that example. That's going to be a vector field. Okay, the set of all polynomials of degree 3 or less. So a generic element in that set, they're polynomials. So you will have a naught, your constant term, plus some scalar times x to the first power, plus some scalar times x to the second power, plus some scalar times x to the third power. Okay, and each of these can elements or scalars can be any real number, where a sub I is any real. Okay, even A3 is, because look at the way that the set is described. Polynomials of degree 3 or less. So if A3 is 0, you're looking at a quadratic or maybe even a line, but that is of degree 3 or less. Okay, is it possible to take a linear combination of 2 degree 3 polynomials and get something that's not degree 3? Okay, so can I take an f of x that looks like this and a g of x that looks like this and get something that's not ai is any real, and get something that is not degree 3? Think about it. I think I have an example for you. Let's let f of x be x cubed plus x squared plus x plus 1, and let g of x be the function x cubed, and let the linear combination be 1 times f of x, let's say h of x is 1 times f of x minus 1 times g of x. Okay, remember, we're looking at this as though they were vectors. So that's like taking 1 times f of x. Okay, what would the function f of x look like if it were in vector notation? It might look like something like 1, 1, 1, 1. Minus 1 times g of x. And g of x might look like 1, 0, 0, 0. Okay, where that is the coefficient on x cubed, x squared, x, and the constant term. Okay, and if you were to take a look at the difference of these two vectors, you would get something like 0, comma, 1, comma, 1, comma, 1, which corresponds to the function x squared plus x plus 1 as h of x. So it is possible to take a linear combination of degree 3 polynomials and get something that is not degree 3. Okay, and that's an example of such. Vector spaces that we are going to use. Okay, obviously we'll look at Rn. We'll look at m by n matrices. We'll look at continuously differentiable functions n times over some interval. And we'll look at polynomials of degree n with real inputs. Okay. Just a comment on that. Okay, looking at, I think the most important thing that we discuss, this is a quick overview of this section. The most important thing that we discuss in this section, and the thing that students would struggle most with, is identifying what a generic element in each of these sets look like. Okay, obviously, with number one, vectors in Rn, the generic element is going to look like x naught, x1. Well, I should call this x1, x2, x3, and so on, up to xn, where the x sub I are all elements of the reals. Okay, so you have 1, 2, 3, 4, up to n components of the vector. Each one of those components are real numbers. And that's what a generic element in Rn looks like. What about n by n matrices? Okay, well, that is m rows and n columns. So that looks like a matrix A11, A12, all the way up to A1n. Oops, that's a 1, not I. This is A21, A22, all the way up to A2n. This goes down to ANM1. This is AM2. This goes down to AMN. Where each of the AI sub j is in the reals. There's a lot of examples that we're going to do moving forward where you kind of have to think about these things in the abstract. You can't think of an individual element in the vector space. You have to think of a generic element. And so that's why we're kind of going through this. 3 polynomials of degree n with real inputs. Okay. So polynomial of degree n with real inputs, so p n of x would look like a what? N x to the n plus a n minus 1 x to the n minus 1 plus dot 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 a1 x1 to the first power plus a naught. Oops, a naught. There we go. And where an has to not be equal to 0, but ai is an element of the reals for I equal 0, 1, all the way up to n minus 1. So here, we're drawing a distinction between each of the coefficients on x to certain powers all the way up to n minus 1 versus x to the n, because you can't have a polynomial of degree n if an is equal to 0, because then it's a polynomial of degree n minus 1. So we have to make sure that an is non-zero, but everything else can be anything it pleases. 4. Continuously differentiable polynomials n times over an interval. Now here's the one where the generic element cannot be expressed as easily as in examples 1 through 3. Okay, so this one you kind of have to say it out in words. Okay, f of x where Fn of x is continuous on interval I. And that's about as clean as we can write that set. And you just have to understand, because there's a lot of different functions. I mean, polynomials will work, so will sine, cosine, and e to the x. Well, you can't really write a generic element that has sine, cosine, e to the x, and all the polynomials. So you just represent it by f of x, where f of x is described in such a manner. All right, so these are all the vector spaces that we're going to be using. And again, a vector space is kind of how I described it in the beginning of this notes, Okay, it's a collection of vectors, functions, or matrices that can be added in the same way vectors get added and scaled. Okay, so that's what we're going to understand vector spaces to be. There's 10 properties, but again, we're not going to go over those 10 properties. The next section, 4.3, is a very important one where we get to deal with subspaces of vector spaces. So that's like subsets that behave in the same way a vector space behaves. Okay, and we'll talk about more when we get back. Take care, and I hope you're having a good one.